I want to start today's deep dive with a scenario I think almost everyone can relate to. You're at the store, maybe after a workout, feeling pretty good about yourself. You grab a protein bar, you flip it over, and you see that big number, 20 grams of protein.
Yep.
And you think, okay, I need 20. This has 20. Done. Into the cart it goes.
That's the standard move. We see the number and we just assume that what's on the wrapper translates directly to what our body gets.
Exactly. But after reading through the research you sent me, I have a feeling you're about to tell me that my protein math is, well, completely off. Is 20 grams really 20 grams?
Chemically, in the wrapper, sure. But biologically, once it's in your body, almost certainly not. And that little gap, that difference, is what we're really digging into today.
So all protein isn't created equal?
Not even close. We think of it as a monolith and, a brick is a brick. But that's not how our bodies see it. And this isn't just a small detail. It's a huge shift in nutrition science. We're moving from just counting crude nitrogen,
Just the stuff.
exactly the raw stuff, to a much more precise way of measuring. It's really a battle between an old standard, PDCAAS, and a new, much tougher one called DIAS.
Okay, let's unpack that alphabet soup right away. PDCAAS and DIAS.
Right. PDCAAS is the Protein Digestibility Corrected Amino Acid Score. That's been the gold standard since 1989.
Okay.
But the new system, the one the FAO, the Food and Agriculture Organization, is pushing for, is DIAS, the Digestible Indispensable Amino Acid Score.
And the mission here is to figure out why the experts are changing the rules. Because this isn't just some minor update, right? This actually changes the scoreboard for what we consider good protein.
Oh, it completely flips the leaderboard. And today we're going to find out why a certain kind of pig is the new hero of nutrition research and why measuring digestion in your small intestine versus, well, at the very end changes everything, especially for plant-based foods.
Okay, the very end, I get it. So before we get into the new science, we need to understand what was wrong with the old way. PDCAAS has been around since the late 80s. That's a pretty long run.
It was. And to be fair, it was a huge step up from what we had before. Before 89, the method was called PER, Protein Efficiency Ratio.
And how did that work?
We fed protein to growing rats and measured how much weight they gained.
Rats. We were basing human nutrition on rodents.
Yep. Growing rats. And there was one massive fundamental flaw.
What was it?
Rats have fur. A lot of it. And humans, well, most of us don't.
Okay, I feel like I'm missing the connection. What does a fur coat have to do with my protein shake?
Growing all that fur requires a huge amount of sulfur-containing amino acids, specifically methionine and cysteine. So the rats needed way more of this stuff than we do.
So if a protein was low in those sulfur amino acids,
It got a terrible score from the rats, even if it was perfectly good for a human who isn't trying to grow a winter coat.
so we were judging our food based on a rat's grooming needs. Unbelievable.
Pretty much. So PDCAAS came along in 1989 to fix that. It used human amino acid needs, which was great. But it had its own fatal flaw, a flaw we now call the poop problem.
I had a feeling we were headed there. So PDCAAS measures digestibility by analyzing the end product.
Exactly, measures fecal nitrogen. The logic was simple input minus output. If you ate 20 grams and only 2 grams showed up in your feces, the conclusion was, great, your body must have absorbed the other 18.
Seems logical. If it didn't come out, it must have stayed in.
It sounds logical, but it completely ignores the giant fermentation tank in the middle of your body. The colon.
The microbiome.
That's the one. And those trillions of bacteria, they're hungry. They love nitrogen. So if you eat a protein that's hard to digest, it just cruises through your small intestine where you should have absorbed it and ends up in the colon.
And the bacteria have a feast.
They have a feast, they eat it, they convert it to ammonia, whatever. The point is, by the time the scientists analyze the feces, the nitrogen is gone.
So the evidence has been destroyed, but I didn't get the protein.
You didn't. Your bacteria did. The test gives you credit for protein that your microbiome basically stole from you. It systematically overestimates the quality, especially for plant proteins.
Okay, so that brings us to DIAS. How does it solve the poop problem?
It's simple, really. It just moves the finish line. Instead of measuring what leaves the body, it measures at the ileum. That's the very last section of the small intestine.
And why there, specifically?
Because that's where absorption happens. Biologically, if a protein gets past your ileum, it's game over for your nutritional benefit. It's lost. DIAS measures what your body actually had a chance to absorb before the bacteria could get their hands on it.
It's like a truth serum for protein.
That's a perfect way to put it.
So if we're measuring at the small intestine, it really starts to matter how easily something breaks down. I'm guessing a piece of fish and a handful of raw lentils don't behave the same way.
Not at all. And that's where we get into something called anti-nutritional factors, or ANFs.
Right, I saw that in the notes. This sounds like plants are basically fighting back.
In a way they are. Think about it. An animal can run or fight to defend itself. A plant can't. So over millions of years, they've evolved these sophisticated chemical defenses to stop things, like us, from digesting them.
What kind of defenses are we talking about?
Well, one of the big ones is trypsin inhibitors. Your body uses an enzyme called trypsin to break down proteins like a pair of molecular scissors.
Okay.
These inhibitors, which you find in raw legumes and soy, literally bind to your scissors and stop them from working.
So they tape the scissors shut.
Perfectly put. The protein is right there in your gut, but your body can't cut it up into small enough pieces to actually absorb it.
That's wild. Are there others?
Oh, yeah. You have things like phytates. Think of a phytate like a tiny, powerful magnet. It latches onto minerals like iron, zinc, and calcium and just carries them right out of your body. You eat the mineral, but the magnet steals it before you can absorb it.
And animal proteins.
Yeah.
Meat, dairy, eggs. They don't have these defense mechanisms.
Generally, no. They're biologically similar to us, so they don't have these inhibitors. Their digestibility is incredibly predictable and high, usually over 90%. They don't fight back.
Okay, so we've got the tougher test with DIAS, and we have these resistant plants. Let's see the scores. When you apply this truth serum, what does the hierarchy look like?
It becomes incredibly clear. Dairy is king.
Give me some numbers.
Whole milk powder scores a DIAS of about 1.16. Skim milk powder can get up to 1.31 for adults.
Wait, hold on. 1.31. How can you have 131% of something?
That's probably the single biggest and most important change from the old system. PDCAAS used to truncate the scores. It capped everything at 1.0 or 100%. Even if a protein was amazing, it just got a perfect score and that was it.
So it's like getting 100 on a test, but you couldn't get any extra credit.
Exactly. It treated excellent and absolutely perfect as the same thing. DIAS lets the score go over 100. That 1.31 means milk has a 31% surplus of the essential amino acids your body needs.
Okay, I want to come back to why that surplus is so important. But first, let's finish the scoreboard. Cannibal proteins are topping the charts. What about the plants?
This is where the reality check really hits hard. Cereals and grains. They plummet. Most of them are really low in one specific amino acid, lysine. Polished rice. It scores around 0.37.
37.
Yeah.
That's barely a third of what you need.
Correct. Wheat is in that same ballpark, maybe 0.40 to 0.48. Corn is even lower, around 0.36.
Ouch. What about the ones we think of as protein powerhouses, like beans and lentils?
Legumes do much better. Chickpeas are around 0.83, lentils about 0.75. But they have the opposite problem. They're loaded with lysine, but they're low in the sulfur amino acids methionine and cysteine.
So it's like a jigsaw puzzle where every piece is missing a different edge.
That's a great analogy. But there is one major exception, the one I call the plant unicorn.
Let me guess. Soy.
Soy. A whole soybean scores a DIAS of 0.996. It's basically indistinguishable from animal protein. It really isn't a class of its own in the plant world.
Okay, let's circle back to that surplus idea. Milk is at 1.31. If my body can only use 100%, isn't that extra 31% just waste?
It would be, if you only ever ate milk by itself. But we eat meals, we combine foods, and this is where the math gets really powerful. It's a concept called complementarity.
This is the whole rice and beans idea, right?
It is, but now we can prove it with precise math. Think of it like a bank account. Wheat is in lysine debt. It has a score of 0.4. Milk has a lysine surplus, a score of 1.31. When you eat them together, the milk's surplus pays off the wheat's debt.
So because the score isn't capped at 100, we can actually balance the books.
Precisely. We can see that surplus and use it. We can blend a 1.31 food with a 0.4 food and engineer a final product that hits a perfect 1.0. You could never do that with PDCAAS because it hid the surplus.
So a food scientist can literally play Tetris with these ingredients.
You can design perfect protein blends. There's a great example with wheat and potatoes. Wheat is low quality, but potato protein, surprisingly, is very high quality.
Potatoes? I thought they were just carbs.
There's not a lot of protein in them, but what's there is excellent. And if you blend wheat and potato protein at a 30-70 ratio, you can create a blend with a perfect DIAS score of 1.0.
That's incredible. It's not about finding one superfood, it's about smart combinations.
That's the future, precision blending.
Now, what about what happens in the kitchen? We talked about those anti-nutrients, the tape scissors. Can I just cook them out?
For the most part, yes. Heat is a great tool. Take raw sweet potatoes. Their digestibility is only about 52%. You cook them, it jumps to 99%. The heat denatures the inhibitors. It untapes the scissors.
So the solution is just to cook everything really well.
Not so fast. There's a dark side to heat. If you go too hot, you trigger the Maillard reaction.
The browning reaction. On toast, on steak, that's the best part.
It tastes great, but chemically, it can be a disaster for protein quality. The Maillard reaction happens when an amino acid, almost always lysine, gets fused to a sugar molecule under high heat. It binds them together so tightly your body can't break them apart. The lysine is physically there, but it's unusable. You've essentially handcuffed the nutrient.
So if I burn my toast, I'm actually lowering its available protein.
Significantly. Heat is a double-edged sword. It can disable the plant's defenses, but too much can destroy the very nutrients you're trying to get.
So if heat is tricky, what's another option?
You get someone else to do the work for you. Fermentation.
Let the microbes handle it.
Exactly. You use friendly bacteria or yeast to pre-digest the food. They break down the tough plant structures and eliminate the anti-nutrients. It's why foods like tempeh or natto are often nutritionally superior to just plain soybeans.
It's like microscopic chefs doing all the prep work.
That's a good way to look at it.
So we have this better system, DIAS. It's more accurate. It respects biology. But you mentioned there's a hero of this story we haven't talked about yet, the pig.
Ah, yes. The growing pig model.
Why pigs? I mean, we made fun of the rat model earlier. What makes a pig a better stand-in for a human?
A much, much better one. For a few reasons. First, they're omnivores, like us. Their digestive tract, the length of it, the way their colon works, it's remarkably similar to ours.
Okay.
And they eat like us. Rats are grazers, they nibble all day. Pigs eat distinct meals. They are a fantastic metabolic proxy for humans.
So what we see in a pig's ileum is very likely what's happening in ours.
It's the current gold standard. But the technology is moving beyond that, too. We now have non-invasive human studies using something called a dual isotope assay.
That sounds complicated.
It is, but the idea is simple. We feed volunteers a protein that's been labeled with a harmless tracking isotope. Then we can measure their breath and blood to see exactly how much of that protein was actually used by the body to build muscle. It's the ultimate validation.
Much nicer than surgery, I imagine. So I have to ask about the elephant, or maybe the cow in the room here, the sustainability argument.
This is a really challenging part of the conversation.
We're told constantly that plant-based is better for the planet, the protein transition. But if plant proteins are less digestible, how does that math actually work?
It creates a real paradox. It is absolutely true that producing animal protein is resource intensive. It can take, say, 6 kilograms of plant feed to produce 1 kilogram of animal protein.
A 6-to-1 ratio, that's inefficient.
It is, from a production standpoint. But the inefficiency flips when you look at digestion. Because plant proteins have lower DIAS scores, they are biologically inefficient for our bodies. You simply get less bang for your buck.
So to get the same amount of usable protein,
You have to eat more. You can't just do a one-for-one calorie swap. You might need 130 or 140 calories of lentils to get the same amount of absorbable amino acids as you would from 100 calories of beef.
so there's an exchange rate.
There is. In fact, the Health Council of the Netherlands recently increased their protein recommendations specifically for vegans and vegetarians, acknowledging that they need to eat more total protein to compensate for the lower quality.
That has huge global implications.
Yeah.
If we all switch to plants, we might actually need to grow more total food than we thought to get the same nutrition.
Exactly. You save resources on the production side, but you have to account for the inefficiency on the digestion side.
Which brings us all back to the food label on that protein bar. What is the so what for all of us? Is DIAS actually going to show up on packaging?
That is the regulatory battle that's happening right now. The FAO wants the world to adopt diastasis, but the plant-based food industry, well, they're pretty nervous.
Because the scores are going to drop?
In many cases, yes, significantly. For instance, under the new rules, to make a good source of protein claim, a food might need a DIAS score of 75.
And we saw that many lentils and grains are below that number.
Correct. So a product like lentil soup, which could easily make that claim under the old system, might suddenly lose its good source status. And public health experts are torn.
Why is that?
Because they worry it sends the wrong message. Do we really want a food label that implies lentils are bad? They're a fantastic whole food, but their protein is technically lower quality.
It's a conflict between scientific accuracy and public health messaging.
Precisely. The fear is a consumer sees the new label, puts the healthy lentil soup back, and grabs a highly processed burger that scores well on protein but is loaded with things we should be avoiding. Is that a net win?
That's a really tough problem. But hiding the truth doesn't feel like the right answer either.
I agree. The data is the data.
Okay, so to sum up this deep dive, the old system, PDCAAS, was flawed because it gave us credit for protein that was actually being eaten by our gut bacteria.
Correct. It missed the microbiome factor.
DIAAS fixes that by moving the finish line to the small intestine, using pigs as our very helpful stand-ins.
Yep.
And the really big takeaway is that while animal proteins score high, plants can compete if we use this new uncapped math to blend them intelligently.
That's the whole game. It's not about good or bad foods. It's about precision engineering to meet our body's needs.
This has been absolutely fascinating. I will never look at a protein bar, or a pig for that matter, the same way again.
As you shouldn't. And if I could leave you with one last thought.
Please?
We're moving to a world where protein isn't a single noun anymore. The future isn't a simple animal versus plant debate. It's about high-tech, precise blends of multiple sources. The big question is, will our food labels be allowed to reflect that sophisticated math? Or will regulators stick to the old, simple system to avoid confusing people, even if that simplicity is hiding the biological truth?
Are we ready for the truth on our labels, or do we prefer the simple, comforting lie of 20 grams is 20 grams? A great question to end on. Thanks for listening to this deep dive. We'll see you on the next one.
Stay curious.